Today we're going to start talking about gases, right? Yesterday and the day before we talked about the thermodynamic, thermochemistry stuff, and that leads us straight into gases. And so the first thing I want to talk about when it comes to gases is that gases, at least the characteristic of gases, right? Physical properties of gases are all similar, right? Although they're mainly composed of non-metallic elements with simple formulas and low molecular masses, right? So what that means is that a lot of the guys over here that are nonmetals can be gases, right? Like fluorine, chlorine, bromine, helium, neon, oxygen, nitrogen. Those all can be gases, right? They're mostly all non. They're mostly all. I said bromine. Sorry, not bromine. Bromine's actually a liquid, but all the ones that are red, right, are gases, and so they are. Unlike liquids and solids, right, the gases expand to fill their containers. They're highly compressible and they have extremely low densities, right? So you can put a gas into any container, okay? You put a gas into any container, and they expand to fill the container like a balloon. And then they're also highly compressible because so you can squish them down, right? And they have extremely low densities, right? The densities of gases are very low. So two or more gases form a homogeneous mixture because you can't really tell the difference between the two different gases, right, when they're mixed together. Kind of like in our air of our atmosphere right now, right? We have nitrogen and oxygen gas, but you can't see the difference between the nitrogen and the oxygen in our atmosphere, right? And so that's why it's a homogeneous mixture, right? So the things that you need to know for this, right? The things that you need to know for this is that let me get my pen to write real quick. I forgot to get the pen to write right here. Gases, right, always expand to fill their containers. Okay, expand to fill their containers. That's different than liquids and solids. They're highly compressible. Solids are not compressible. Liquids are kind of compressible, but gases are super compressible. And then they have extremely low densities, right? Liquids and solids, on the other hand, always have very high densities, right? And so you got to make sure you know these are the three characteristics of gases right here. Those are the three characteristics of gases. Okay. So my very first question for you is this, right? Which of the following is not a property of a gas? Do they expand to fill their containers? Are they highly compressible, or do they have extremely low densities? Or are all these true? Are all those true? What do you think? You think it's D? That is correct. The answer is indeed D. The answer is indeed D, yes. Gases are definitely, they expand to fill their containers, they're highly compressible, and they are extremely low densities. The answer is indeed D. All right, so here are some common gases, right, that we can study. In addition to like things that we know about already, like oxygen and nitrogen, right? Hydrogen cyanide is a gas. Hydrogen sulfide is a gas. We were talking about before how hydrogen sulfide smells really bad, and so they put it into the gas lines for your stove, right? And that's how you know when you have a leak in your gas line. Carbon dioxide, we breathe out carbon dioxide. Methane, methane is the gas that's in your stove that lights up. Ethylene, propane, like propane tanks for your grill. Nitrous oxide, which is, I believe that's laughing gas. Yes, it is laughing gas right there, right? There's laughing gas. So, did you know that if you breathe in nitrous oxide, you laugh? It makes you laugh, like, ha ha ha. It's kind of crazy. Nitrogen dioxide right here, toxic red brown irritating odor. You definitely don't want to be around that. Ammonia, you smell that a lot when you're using Windex to clean your glass, right? And sulfur dioxide, also colorless and irritating odor, right? So the properties of gases define the state of a gas sample, right? Sorry, the properties that define the state of a gas, right, are these properties right here, right? And so those properties right here, temperature, right? Temperature, which is big T, pressure, big P, big V, which is volume, and then the amount of gas in the number of moles, that's usually N, right? Little n, yes, for number of moles. little n is number of moles. And so every single gas equation, right, every single gas problem, right, that you do in class will involve those. One of these, two of these, or all three, all of these, okay? So you always have to be aware that gas problems will always have a temperature, pressure, volume, or number of moles, okay? They will involve those particular properties, okay? So what exactly is pressure? Well, pressure right here, and this is the physics definition of pressure. You don't need to really memorize that. I'm not going to ever ask you about this because that says the force over an area. We don't talk about force or area in this class, but it is a physics formula. Specifically, it explains this, right? The pressure is the amount of force applied to an area, right? So the force divided by the area gives you the pressure right here. But you don't need to remember this, okay? Physics. Do not need to know this, right? The only thing I just wanted to tell you that it is a physics formula, and I wanted to talk about it, but I'll never ask you a question about this, or I'll never ask you to calculate anything based on the force or the area, right? And so there's also this thing called atmospheric pressure, and that is the weight of air per unit area, right? So it turns out that here on Earth, as we stand here, the pressure of the air and the atmosphere on us is 1 atm, 1 atm, right, or 1 atmosphere, and that changes based on where you are, right? If you're, it changes whether you're higher in the air, like on a mountain, or lower, like in a valley, right? That pressure changes. But we're not super worried about that kind of stuff on Earth. We're worried about the pressure inside of a during a reaction or something like that, or in a chemical sense, right? So, what are the units of pressure? Okay, what are the units of pressure? Well, the units of pressure, the first one is called the pascals, right? And pascals is like 1 PA, right? That's a pascal. And the unit is 1 Newton meter squared. There's also the bar, which is 1 bar equals 10 to the fifth pascals, or 100 kPa, right? The one that we'll probably use the most here is the millimeters mercury, right, and the atmosphere. So the millimeters mercury is equal to torr. They have the same numbers, right? And these units are literally the difference in the height of measured millimeters in a column connected by a mercury, and that's called a barometer. So this right here is called a barometer, and what it does is that it detects and describes pressure. And so what you have here is a little glass dish, and in this glass dish there's some mercury, right? There's mercury, and remember, mercury is like a metal, but it's a liquid metal, you know. And so you can put a tube into the mercury, right, that has a vacuum in it, and the tube will suck up the mercury, right? The tube will suck up the mercury into the tube because of the vacuum, right? And so what happens is that the more the pressure is outside, the more it will push down on the mercury in the little glass dish, and then it will push up the mercury into the tube. And so there's this height right here, and the height that the mercury goes is the pressure that's exerted by the atmosphere or whatever you're trying to measure, right? So literally it's a height. That's why this unit is called millimeters mercury, because this millimeters mercury part is literally the height that the mercury changes in this tube as the pressure changes. Right, as the pressure changes. Okay, so you can use that height there to indicate pressure. And so we have some more conversions here that we have to deal with, right? 1 atm, right, equals 760 torr, which is actually the same thing as 760 millimeters mercury, which is the same thing as 101.325 kilopascals, or 1.10325 bar, right? But the ones that I want you to focus on the most is the ATM right here, right? and then the 760 millimeters mercury. Okay, so just remember this is the important one. 1 atm equals 760 millimeters mercury. Okay, that's the important one. Remember. Okay, that's the one that you should know because we'll use that in calculations a lot. Okay, we'll use that in calculations a lot. All right. So again, the units of pressure are the Pascal, the bar, the millimeters mercury or torr, and then the atmosphere. Okay. So the next question here is this here, Hanny. Which of the following is not a unit of pressure? Which of the following is not a unit of pressure? Which of the following is not a unit of pressure? What do you think it is? D, like dog, right? D. Yes, that is correct. The answer is indeed all of them. The correct answer is D. Good job. Good job. Good job. So we can use another instrument called the manometer, right? And the manometer can also detect pressure too. So here we have the pressure of a gas, okay? And then we have the pressure of the atmosphere, right? And as the pressure of the atmosphere increases, it pushes down on the liquid here, right? And so as it pushes down on the liquid here, it changes the height, right? It changes the height. And if it changes the height, you can detect the pressure. And so you can detect the pressure using this equation right here. The pressure of the gas, right, equals the pressure of ATM plus the height, right? Plus the height. So you can do that. And so if you, for example, if the pressure is strong enough, it can push down the liquid down to about halfway here, right? And you can measure the distance, right? And then you can figure out the pressure that way too. But I'm not going to ever ask you to use that equation, right? This is not that important. But there is another way to do it, and that's called the manometer, right? And so of course, again, this is the thing that we use to measure the difference between atmospheric pressure and the gas inside of a vessel. But I'm not going to ever ask you to do that, so don't worry about that so much. I just wanted to show you the instrument, okay? And then so there are indeed, and we talked about this in the last slide, not last slide, the last lecture, right, about thermochemistry. We normal atmospheric pressure at sea level, right, is referred to as standard atmospheric pressure. And if you remember back in the thermochemistry lecture, I said that the STP, right, which is stands for standard temperature and pressure, right? STP, standard temperature and pressure, right? The temp was 25 degrees Celsius, right? And then the pressure was 1 atm, right? Remember I said that yesterday, right? And so standard atmospheric pressure is what at 1 atm, right? And that's at sea level, right? Whatever the height of sea is. So us here are at sea level. And so our standard temperature and pressure are 1 atm, 25 degrees, right? So a lot of calculations might use that. And so then that takes us to talking about all the different gas laws, because we have a lot of them. We have a lot of different gas laws, okay? And so the first gas law to talk about is called Boyle's Law, right? The first gas law is called Boyle's Law, right? And the important thing about the Boyle's Law is that it says the pressure of a gas is inversely related to the volume when the temperature is constant, right? And so the picture you see here is showing that, okay? What it means here is that as the pressure, right, as a pressure, this got a lot of volume right here, right, which is 4 liters. and you're at 1 atm. But then when you squish it down from 4 liters to 2 liters, you're at 2 atm, right? And so as the volume goes down, the pressure goes up. Okay? As the volume goes down, the pressure goes up. I will actually give you this on a test, but you need to know what it means, right? I will give you the equation on a test, but you do need to know what it means, right? So what it means is this. If the volume decreases, the pressure increases. That's the important part. Like, because I might ask you a question on the test that was like, you have a system where you have a volume and a pressure, but you decrease the volume. What happens to the pressure? It goes up, right? Okay. So this is the part that you have to memorize right here. Volume decreases as the pressure increases, right? And again, like I'll provide you equations on the exam, so you don't have to actually have this equation memorized, but you need to know what it means. Okay? So this is how our lungs work. How do we breathe in, right? How do we breathe in? Okay? So when we breathe in, we our diaphragm right here, right, goes down, right? It goes down, and then we suck in air, right? And so the rib cage expands, and we can get more air inside, right? So we're increasing the volume. And then when we exhale, right, the rib cage gets smaller, and the diaphragm relaxes, and everything moves up, and the air gets exhaled, right? So that's the practical application of Boyle's law. Okay, that's Boyle's law. So remember, okay, Hanny, and everybody else that's watching this, Boyle's law says this, right? If the volume decreases, the pressure does what? Increases, right? Okay. So next, we have Charles's law, right? So Charles's law is about the temperature and the volume, okay? If you see here, we have a temperature of 200 Kelvin, right? Which seems like it's not that hot, but it's pretty hot. And then we have a liter, right? I mean, a volume of 1 liter, okay? If we increase the temperature to 400 Kelvin here, the volume goes up to 2 liters. So in Charles's law, right? In Charles's law, when the temperature of a gas increases, what happens? The volume increases, right? So that's the important part here. Charles's law is as the temperature of a gas increases, the volume increases, right? The volume increases, okay? And again, this equation I'll give you on a test, but the part that you need to definitely remember is what it means, right? Increase the temperature of the gas, you increase the volume. And so the example of this would be this. Here we have a balloon, right? And as the balloon gets hotter, the balloon gets bigger, right? But then as the balloon gets colder, exactly, it gets smaller, it shrinks. Okay? So that's Charles's law. Okay? Then we have Gay-Lussac's law, right? This is Gay-Lussac's law. And this one relates temperature and pressure. Okay? So here we have a temperature of 200 degrees Kelvin, and we have a pressure of 1 atm. But if you increase the temperature, right, to 400 degrees, the pressure also goes up to 2 atm, right? So what does Gay-Lussac's law say? It says that when the temperature goes up, the pressure goes up, right? When the temperature goes up, the pressure goes up. Okay? When the temperature goes up, the pressure goes up. Okay? So Gay-Lussac's law says this: when the temp goes up, the pressure goes up. Does that make sense? Right? When the temperature goes up, the pressure goes up, right? And so this is a good example of this would be here, right? Here at sea level, right? Here at sea level, the boiling point of water is 100 degrees Celsius, right? where the pressure is, like in the mediums, right? It's mediums. It's 1 atm, which is medium. It's 100 degrees, right? But here at the Dead Sea, which is a valley, the temperature goes up for the boiling point of water. And then here at Mount Everest, where the pressure is very low, the boiling point goes down, right? So again, temperature goes up, pressure goes up. Temperature goes down, temperature goes down. Sorry, temperature goes up, pressure goes up. Temperature goes down, pressure goes down, right? So Gay-Lussac's law says this: when a temperature goes up, the pressure goes up too. Okay? Pretty simple, right? So what happened then was that they combined. Uh, so what happened was like Gay-Lussac's law of combining volumes, right? They combined a lot of the gas laws, right? And when they combined the gas laws, it led to this right here. It led to what we call the combined gas law. Okay, and so the combined gas law looks like this. It says P1 B1 divided by T1 equals P2 V2 divided by T2, right? So what can happen here is that if I give you a problem, right, and we'll work some problems tomorrow, since this is kind of a short lecture. We'll probably spend most of the day tomorrow working problems, right? If I give you a pressure, an initial pressure, an initial volume, and I give you an initial temperature, and I ask you to figure out what the new volume is, right? But I give you this and this, you can solve for V, right? Because it's the only one that's missing a number. Okay, so given an initial volume, initial pressure, initial temperature, and given a final pressure and a final temperature, you can solve for the final volume, right? Does that make sense? And or you can go backwards. If I give you the final pressure, the final volume, the final temperature, and then I give you the original temperature and the original volume, you can find what? The original pressure, right? So the key here is to be able to go through the problem and find those numbers and put them in the right places, right? But again, I'm not going to make you memorize that. I'll give you that on a test, but you just have to remember how to use it, okay? You just have to remember how to use it. Okay, so let's review all these just one more time, okay? Just one more time. Starting off with Boyle's law, right? If we are at constant temperature, right, and a constant number of gas molecules, right, then when the volume decreases, the pressure increases, okay? So Boyle's law, volume decreases, pressure increases, but what stays the same? The temperature and the number of gas molecules, right? And then the next one, oops, and the next one, right? Charles' law says that when the number of gas molecules and the pressure stays the same, then the temperature gas increases, the volume increases, right? So this one is based on the fact that you have the same number of gas molecules and the same pressure. Okay, Charles's law. And then Gay-Lussac's law says if you have the same volume and same number of gas molecules, that's constant, then when the temperature goes up, right, the pressure goes up. Okay? Okay? So, one more time. This is where we have constant temperature. But Boyle's law is constant temperature, right? And then Charles's law is when we have constant pressure, right? And then, oops, there we go. And then Gay-Lussac's law is when we have constant volume. Okay? So, your next question is this. Which of the following gas laws is dependent on constant pressure? Okay? Which of the following gas laws is dependent on constant pressure? Go through your notes. You'll see it, I promise. What do you think? Which law? Boyle's, Charles, Gay-Lussac's, or all of the above? Yes, that is correct. The answer is B, Charles's law. Right? Because that one depends on constant pressure. Okay? Remember the Gay-Lussac's law is dependent on constant volume, and the Boyle's law is dependent on constant temperature. Okay? Good job. Good job. All right, so the next law we have is called Avogadro's law, right? It's called Avogadro's law. And so here, both temperature and pressure are constant, right? Both temperature and pressure are constant. And what it says is that when you have uh, 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 a certain number of moles of gas, right, which is 1 mole of gas here, you have a volume, which is 1 liter, right? But if you increase the number of moles, what also increases? The volume, right? So as moles of gas increase, what happens to the volume of the gas? Yes, yes, it increases as well, right? So Avogadro's law says this, okay? As number of moles increases, the volume also increases. Make sense? Right? That's what Avogadro's number says, right? And so we have another conversion that we can use right here when we're doing dimensional analysis, trying to figure out different things with the gases, right? So one mole of gas is always going to be 22.4 liters. Okay, 1 mole of gas will always be 22.4 liters, right? So you can use it this way, where you say 1 mole of gas is over 22.4 liters, or you can say 22.4 liters is 1 mole of gas, right? And you just put that into your dimensional analysis when you're figuring something out, right? When it comes to gases. And again, we'll do some practice problems tomorrow. Okay. All right. So this puts everything together now. We have this thing called the ideal gas law, right? Where we have Boyle's law, which says constant number of moles and constant temperature. Charles' law says constant number of moles and constant pressure, right? Avogadro's law says constant pressure and constant temperature. We put it all together and we get this equation right here, which is called the ideal gas law. PV equals nRT. You'll use this a lot. That's important, right? Ideal gas law. Okay. So in PV equals nRT, you already know that the P stands for pressure. You already know that the volume stands for volume. I mean, the V stands for volume. You already know that the T stands for temp or temperature. You know that the N stands for number of moles, right? What is the R? Huh? What is the R? What is the R? Well, it turns out the R is called the ideal gas constant. Okay? The ideal gas constant. Okay? That's called the ideal gas constant. That's what R is. That looks like a K. I should fix that. It's R. There we go. Okay? The ideal gas constant. So what is the ideal gas constant? right? Well, here it is. This is the ideal gas constant, right? So there's your R, right? The ideal gas constant. And that is this right here in PV equals nRT, right? Ideal gas constant. And there are these values right here. There are these values with these different units. They're either 0.08206 liters ATM mole Kelvin, or they're 8.314 joules moles Kelvin, or it's some of these over here. Let me just tell you, right? The one you'll use most commonly with PV equals nRT is this one. Okay? The one that you'll use, right? The one that you'll always use, most of the time use with PV equals nRT is this, the 0.08206, right? Okay? This is the important one right here. You use this sometimes right here, the second one, sometimes, right? But the other one, this first one here, will be the one that you use the most, okay, with PV equals nRT. Does that make sense? Right? So we could even take it a step further, right? We can take it a step further and actually go through and just do some equations and some derivations and substitutions with PV equals nRT and figure out what the density of gases are, right? So you can actually use this right here, where the density of gas equals MP over RT, all right? And so again, this D right here is density of gas, and then R, right, which is ideal gas law, 0.08, I forgot already what it was, 8206, 206, right, and then this is temp, and this is pressure, okay, and so then what is the big M right here? What is the big M right here? Well, the big M here, right, doesn't stand for molarity, but it stands for molecular mass, right? Big M is molecular mass. And so that's big M goes right there. Actually, let me let me do that again. That's not a good arrow. It gets confusing. There we go. There we go. So that big M right there goes right there, right? That's molecular mass. So what does that mean? That means if you have the pressure of a molecule, right, of a gas, you have the temperature of a gas, you have the ideal gas law, which is right there, right? Ideal gas constant, rather, right? And then you also have the molecular weight or molecular mass of the gas, which you find from the periodic table, right? So say it's oxygen, right? And if it's oxygen, then it's O2. So it's 16 times 2, which is 32, right? And you put the 32 in there for the molecular weight or molecular mass, you can figure out the density of the gas. Get it? Right? You can figure out the density of the gas, right? So let me write that again, right? If the gas, I'll do for example, right? If the gas is O2, right? And O2's molecular mass, oops, let me erase that. I wrote the wrong letter. we go. Erasing is a lot harder than writing, let me tell you. Right? And the molecular mass of O2 is 16. No, not 30. I messed up again. 32. No, that's not right. Let me erase that again. It's 32. I say 32, but I write something else. It's so crazy. So crazy. Here we go. Let me try that again. There we go. I won't mess up this time, I promise. There we go. Okay, so in the molecular mass of oxygen is 32 grams per mole, right? Then all you have to do is put that in there for the big M, right? And now you can solve for density. Solve for D, right? You can solve for density. So given the fact that if you have the pressure of the oxygen, the temperature of the oxygen, and then the ideal gas constant, and you have the molecular weight of the oxygen, you put it all in there, and now you can solve for D, right? Which is density. Does that make sense? Yeah. So here are a couple other ones, right? We have here, okay, so this is the one we just did right here, right? Density, you can figure out the density using the molecular mass, right? But say you had the density, and you had the pressure, and you had the temperature, and you had the ideal gas constant, then you can figure out what the molecular mass is, right? You can solve for any of those things. And then, so you can also use it this way too, where if you have the molecular mass, right? And then you have PV and RT, of course, because R again is the ideal gas constant. T is the temperature that will be given to you. Volume will be given to you. P will be given to you, right? Then you can solve for M. And if you look at what M is the number, is the mass itself, right? It's just the mass of the gas, right? So that's little m. Right? So if you have the molecular weight of the gas, and you have the ideal gas constant, the temperature, the pressure of the gas, and the volume of the gas, you can figure out what the mass of the gas is, right? Cool stuff, right? Cool stuff. And so, right, gas data for nRT, right, if you have gas data for N, the number of moles, you can use PV equals nRT to figure out the number of moles of reactants and products. And then from that, you can answer, right, what the P is, the V is, or the T is, right? So again, the ideal gas equation is super helpful, right? The balanced chemical equation tells you the relative amounts of moles in the reaction, whether the compared materials are products or reactants. And so, of course, you can use the PV equals nRT, and it really helps you out with that, right? Because it's very helpful, okay? We can relate volume and gases as well, okay, using PV equals nRT. All right, so here's your next question. In the ideal gas law, PV equals nRT, what does the little n represent? Huh? Yes, that is correct. Good job. This is a pretty easy lecture, right? Number of moles. That's correct. Okay. Number of moles. All right. So that takes us to talking about. Oh man, we're talking about Dalton again. Dalton's so famous. He's everywhere. So Dalton has this thing called the law of partial pressures, and what it says is that if you have a number of moles of a gas, of one gas, and then you get the number of moles of another gas inside one container, right? You can get the total gas pressure. So the equation is this. The equation is the total pressure equals the partial pressure of gas one, partial pressure of gas two, partial pressure of gas three, and so on, however many gases you have. So notice here, right? If we have 1 mole of nitrogen gas, it is 1 atm, okay? If we have 0.4 moles of O2 gas and 0.6 moles of helium gas, you add those two together and you get 1 mole of gas, and it's still what? in 1 atm. Exactly. Here we have zero point 0.5 moles of gas, of oxygen gas, zero point 0.3 moles of helium, zero point 0.2 moles of argon. We add those all up to each other, and we still get 10, or 1 rather, get 1, which is 1 mole, and what is the pressure? Still 1 atm, right? So to make things short, right, the total pressure, the total pressure is equal to the sum of all the partial pressures. Does that make sense? You add up all the partial pressures, and then you'll get the total pressure. Then you get the total pressure. Okay. Any questions so far, or does it seem pretty simple so far? Pretty easy to understand, right? Okay. So then let's talk about the mole fraction. Okay. Let's talk about the mole fraction. Okay. Because each gas in a mixture acts as if it's alone, we can relate the amount of mixture to partial pressures, right? And so this is just PV equals nRT, right? And it's you use it to figure out the ratio of each gas, right? So the PV equals nRT of one gas over the PV equals nRT of the other gas. But all that does is lead you to this. It's the mole fraction, which is this cool little X symbol right there, right? That's the mole fraction, right? That's the mole fraction. And so the mole fraction here, right, is equal to the number of moles of compound 1 or gas 1 divided by the total, right? The total number of moles. Does that make sense? Okay, so if we go back to this over here, let's use this one right here as an example. Okay, we'll use that one right there as an example. And we'll say, oh, what percentage of this gas is oxygen, right? What percentage of this gas is oxygen, or what is the mole fraction of that gas mixture, right? So we see here that it says 0.5, right, is oxygen, and then the total is what? 1 atm, right? And so all you have to do is say x equals 0.5 divided by 1 atm. And that equals the mole fraction, right? Does that make sense? So that should give you 50%. That should give you 50%. Does that make sense? Pretty simple, okay? Not too hard yet, right? Not too hard, okay? Not too hard. You can also do this with the pressure too, right? You can do this with the pressure too, where you have the pressure 1 equals to the ratio of the number of moles of the gas, the partial gas that you have, over the total gas, right, times the total pressure, and that equals the mole fraction times the total pressure, right? That's the mole fraction times the total pressure, right? So you can do it with pressure as well. That takes us to the kinetic molecular theory, okay? Takes us to the kinetic molecular theory, right? What does this law tell us? It tells us that in nature, right, gases, look at them. They're bouncing around by themselves, right, in straight lines, okay? So law tells us what happens in nature. Each of the gas laws we have discussed tells us what we have observed under certain conditions. Why are these laws observed? We will discuss the theory and explain our observations. Okay, so if you see this picture here, what you see is gas molecules bouncing back and forth, right, inside of a container. They go in very straight lines, okay? They go in very straight lines. They're going very fast, okay? And they do it randomly, right? They do it randomly, okay? They do it randomly. So here are the main tenets of the kinetic molecular theory, right? The first one is that gases consist of large numbers of molecules that are in continuous random motion, which is not the important part right there. Remember that it is random motion, right? Gases move randomly, right? So if you look back at this picture here, the gases are bouncing around very randomly, right? They don't have like a set, where they're supposed to go. They just move around randomly, all right? And then the next one is the combined volume of all the molecules of the gas is negligible relative to the total volume of the gas which is contained, right? So, excuse me. It doesn't matter what what the combined volume of all the molecules of gas is, right? Relative to the total volume of the gas in which is contained. So it's more important that you know what the volume of the gas is contained in, right? Inside the bottle. It doesn't matter what it is, what the volume of the gas, all the molecules of the gas together, but what they're in is more important. Okay? And then this right here, the attractive and repulsive forces between gas molecules is negligible, right? So both of these things means that gases they move around independently and they bounce around, right? And randomly, okay? They try not to interact with each other. Or they don't even, they do, but they don't act on each other enough to affect each other, right? Then number 4 is that the energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time, right? As long as the temperature of the gas remains constant, right? So the gases, right, when they're bouncing around, right, they can hit each other, right? But if you don't change the volume, if you don't change the temperature, right, the amount of energy in the entire system stays the same, right? It stays the same, okay? Kinetic energy stays the same, right? And so that means then that the average kinetic energy of the molecule is proportional to the absolute temperature, right? Which means that the energy inside the gas molecules, right, is dependent on the temperature, right, or proportional to the temperature, right? The higher the temperature, the more the energy in the gas. Does that make sense? The higher the higher the temperature, the more the kinetic energy in the gas. That's why a hot air balloon works, for example, right? All right. So, which of the following then, right? Which of the following is not a tenet of the kinetic molecular theory, right? Is it they're in random motion, right? Or is it it's more important to it's relative to the total volume which the gas is contained? Or is the attractive and repulsive forces between a gas are significant? Or are all these correct? Which one is it? Which one is the one that is not true? Gases move in random motion, right? The volume is negligible of all the gases. It's more important about what the gas is contained in, right? The volume that the gas is contained in. Or is it that the repulsive and attractive forces are significant between gases? Huh? Yes, that's correct. Why is it C? Yes, exactly. Are negligible. Good job. Good job. Good job. So, the question might be, wow, we're almost done with this lecture. We're almost done with this lecture. The question is then how fast the gases move, right? Well, again, the temperature is related to the average kinetic energy. It should say energy there. I don't know why it didn't have a word there. Kinetic energy. There we go. Kinetic energy. Okay. Individual molecules have different speeds, right? This figure up here shows you the 3 different speeds, right? The UMP is the ones that are most probable. UAV, or the average speed of the molecules. The URMS is the root mean squared of the average speed of the one associated kinetic energy. But all this really means is, oh man, that's a really small slide. Really small. Can you even see what that says? I can't see what that says. That's really hard to see, isn't it? Yeah, don't worry about this so much, because I'm not gonna ask you a question about this, and especially since I'm gonna have to fix that. That's a really small. Yeah, that's really small. So don't worry about that right now, okay? Don't worry about that. Okay. Um, you can actually, what you can is determine the mean squared of the speed, right, of the gas using components of the ideal gas law, right? Where if you have the square root of 3 times the ideal gas constant, the temperature, and the molecular weight of the mass, you can figure out, right? You can figure out what the kinetic energy is for the molecule, right? The UMS, the URMS, right? Which is the root mean squared associated with the kinetic energy, right? And so the interesting thing about this then is, again, I'm not going to ask you to do this on a test or anything like that, right? The interesting thing about this is that based on the question, if a gas has a low mass, speed will be greater than a mass that has a heavier mass, right? So gases that are lighter go faster, right? And gases that are heavier go slower, based on this equation right here, right? So that's interesting. That's very interesting. Okay. All right. So then here's a couple of vocabulary words about how gases move. Okay. A fusion, right, is the escape of a gas molecule through tiny holes of an evacuated space, right? That's effusion. And then diffusion is the spread of one substance throughout a space or a second substance, right? So if you see here, right, we have here like the gases are all up here, okay, and then there's this little filter down here, okay, and there's little tiny holes, and you can see that the gases are coming through, not all at once, but they're going through the little holes, right? And that's called effusion, right? That's called effusion. And diffusion is when you just have the gas just go through all the space all at once. Okay? Okay, so then we have this thing called Graham's law, and it describes diffusion and effusion, right? What it says is that the lighter gas always has a faster rate of speed, which you said that a second ago, right? We said that before, right? Graham's law relates the molar mass of two gases to the rate of speed, right? And so the lighter gas always has the faster rate of speed. That makes sense, right? And so you can see here that here we have argon in a balloon, right? And we have helium in a balloon, and the helium is up there, and the argon is down there, right? Okay, and so, and of course, argon is down here, right, on the periodic table, and helium is up there, so argon is definitely heavier. See, so, but then eventually, what happens, right? Eventually, what happens is that the helium will leave the balloon, right? The helium will pass through and leave the balloon, and as the helium leaves the balloon, it starts to sink, right? So have you ever gotten a balloon before and you just left it there and it starts to shrink, right? So that's what's happening here with the helium, right? And so as the helium starts to leave the balloon, it starts to shrink and then it sinks, right? And the interesting thing about that is that part of the reason why the helium can leave the balloon so easily is because it's so much smaller, right, and lighter than the argon, and so it moves faster, right? And so it can leave the balloon real easily, as opposed to argon. And then, so that takes us to talking about real gases. So when I was talking about earlier with ideal gases, right? Ideal gases are going to be what you will do the most calculations on, right? But in the real world, there's real gases, and they don't act like ideal gases do. Okay? So in the real world, the behavior of gases conforms to the ideal gas equation only at high temperature or low pressure, right? Even the same gas will show wildly different behavior under high pressure and different temperatures, right? So now we have to think about what will affect uh, the certain properties of a gas, right, at real world temperatures or real world conditions, right? So here are some deviations right here, right, from ideal gas. Okay, here we have ideal gas in an ideal gas, right, where where the gases only bounce off the walls, right? And they don't affect each other that much. But in real life, a real gas will bounce off the walls, but they also will affect each other a little bit, right? They will affect each other a little bit, right? So the assumption made in the kinetic molecular model, right? It says a negligible volume of gas molecules themselves. There is no attractive forces between them, right? And you break down at high temperatures or low temperatures, right? So if you have a high temperature, if you have a high pressure or a low temperature, it turns out that real gases do start to interact with each other. They don't just bounce off the walls like in an ideal gas, right? Does that make sense? An ideal gas just bounces off the walls, right? But if you bring the temperature to high pressure to low temperature, they will bounce off the walls, but they will also interact with each other as well. Okay, they will also interact with each other as well. Okay. All right. So the way that we correct what we call non-ideal behavior, right? The way that we correct for non-ideal behavior of gases is we use this thing called the van der Waals equation. Okay? We use this thing called the van der Waals equation. The van der Waals equation looks a lot like the ideal gas law, right? Or the ideal gas equation. It still has nRT right here, right? And it also has V there for volume and pressure, right? But it puts in these things for the ideal, for the van der Waals gas constants, right? It puts in things for the van der Waals gas constants, okay? And so now, if you're going to figure out how a real gas acts, you'll have to look it up. And then, so P is fine. Pressure, you'll get a pressure. Volume is squared this time here. But here you have to add in the van der Waals equation. Sorry, the van der Waals constants, right? You still have to n for the number of moles squared, but you have to multiply that by A, which is right here, right? A. Let's say we're doing this, right? If we were doing, in addition to doing the ideal gas constant and the ideal gas law, right? You'd add in this A here, which is the 0.0341 into that A right there, okay? And then for the volume, you have to subtract the number of moles again. You have to subtract from the volume the number of moles times B for helium, which is right there, right? And so, if I gave you a problem where I asked you to figure out any of the gas properties using the real gas law or the van der Waals equation, helium, right? You have to take this here, A, from the chart, and plug it in, right? And then you have to take B from the chart and plug it in there, right? Yes, the rest of it is moles, right? And then volume, P. And all that stuff is still the same, right? So it's almost like using the ideal gas law, right? But the real gas law or the van der Waals equation, right, just has you putting in these into the equation the corrections with the van der Waals constants, and the van der Waals constants are on this chart. And so the A here, that's a part of the pressure term, right? That A is the A that's right here for in this chart, right? And if I'm helium, then it's going to be the 0.0313. For here in the volume term, right? In the volume term, you have to put the B there, multiply by the B right there with the number of moles, and that one's B right there for helium right there, right? So that there, right? So it's just the same thing again. It's just an equation. You just got to remember the difference between me asking you a gas property using the ideal gas law, right, or the ideal gas equation, and you solving for a gas property using the van der Waals equation, which is the real gas, right? Just remember that the van der Waals equation is for real gas behavior. Behavior, right? Not ideal gas. Okay, not ideal gas. Okay, does that make sense so far? Yes. Yes. And then, so the last thing to talk about is this question: which variable from the van der Waals equation represents the van der Waals constants? Is it A, which is A, B, which is B, N, which is, or C, which is N, or both A and B for D? Which one of these is the van der Waals constants? D? Yes. D, both A and B are van der Waals constant. Yes, that's correct. That's just number of moles again. Right? So correct. Good job. And that is the end of the lecture for today.